Okay, take a look at this. This simple little box, it's honestly one of the most powerful tools in all of medical research. It's called a 2x2 contingency table, and it's the engine that helps scientists turn, just a pile of raw data into life-saving insights about risk. So today, we're going to build it piece by piece and really demystify it.
But let's start with the big question. How do we even do this? When a researcher has a hunch, right, like they suspect that a certain behavior might be causing a specific health problem, how do they get from that hunch to actual hard evidence? It's the question that drives so much research, and believe it or not, the answer starts with this simple, brilliantly organized box.
So here's our game plan. We'll start with the basics, what we mean by exposure and outcome. Then we'll get into the super strict rules of setting up the table. After that, we'll sort our data into the 4 key cells, and finally, we'll use all that to calculate absolute risk and figure out what it's actually telling us.
All right, first things first. Before we can even think about building our table, we have to be absolutely crystal clear on the 2 things we're trying to connect. In the world of epidemiology, we call these the exposure and the outcome. Think of it this way. The exposure is the potential risk factor we're investigating. It's the thing we're studying, kind of like the independent variable. On the other side, you've got the outcome. That's the health result we're measuring, like a disease, the dependent variable. The classic example that makes this super clear, studying smoking as the exposure and lung cancer as the outcome. And this is exactly why it's called a contingency table. The name is actually pretty logical when you think about it. We're using this tool to see if the outcome, in our example, getting lung cancer, is contingent upon the exposure, which is whether or not a person smokes. It all connects. Now you might be thinking, okay, it's a grid, I can just toss some numbers in there. But nope. The 2x2 table is very, very strict. The structure is everything. And there are some non-negotiable rules you absolutely have to follow if you want to get the right answers. And here they are. Rule number 1, exposure status, so did you smoke, yes or no, always goes on the horizontal rows. Rule 2, outcome status, did you get lung cancer, yes or no, that always goes on the vertical columns. And rule 3, which is just as important, for both of these, the yes category has to come before the no category, every single time. So once you apply those rules, this is the blueprint you get. Exposure yes/no on the left, making our 2 rows, and outcome yes/no across the top, making our 2 columns. This is it. This is the only way you can set it up. And here's why it's so critical. As this quote from Lecterio Medical makes perfectly clear, you have to pay close attention. Because if you set up the table any other way, if you flip the axes or you mix up the yes-no order, the formulas we're about to use, they just won't work. You'll get gibberish. You'll get the wrong answer every single time. Okay, great. So with our structure totally locked in, we can move on to the next step, which is taking everyone in our study and sorting them into one of these 4 empty cells in our table. We give these 4 cells labels, A, B, C, and D. You can think of each letter as just a placeholder for a specific group of people, representing every possible combination of getting the exposure and having the outcome. And this slide right here is what translates those letters into real people. So cell A, that's everyone who was exposed and got the outcome, are smokers who developed lung cancer. Cell B is for people who were exposed but did not get the outcome, so the smokers who stayed healthy. Cell C is for folks who were not exposed but got the outcome anyway, the non-smokers who still got lung cancer. And finally, cell D is our group that was not exposed and did not get the outcome, our healthy non-smokers. All right, now for the really fun part. With everybody all sorted into their proper boxes, we can finally start doing some math. And our very first calculation is to find something called the absolute risk for our different groups. So what even is absolute risk? Well, to put it simply, it's just the chance that someone in a specific group will experience the outcome. You can also think of it as a measure of incidence, basically the rate of new cases popping up in that group. First up, let's calculate the absolute risk for the people who were exposed. In our case, the smokers. The formula is pretty simple. It's A divided by the sum of A plus B. And you can see the logic of this right here on the table. We take the number of smokers who got lung cancer, that's cell A, and we divide it by the total number of smokers in our study, which is everyone in cell A plus cell B. And boom, that gives us the risk of getting lung cancer if you are a smoker. Of course, to know if that risk is actually high or low, we need something to compare it to, right? So we do the exact same calculation, but this time for our unexposed group, the non-smokers. And the formula, as you might guess, is C divided by the sum of C plus D.
And again, the table makes it perfectly clear. We take the number of non-smokers who got lung cancer, cell C, and divide that by the total number of non-smokers in the whole study, which is cell C plus cell D. And that gives us our baseline risk of getting lung cancer if you are a non-smoker.
Okay, this is it. We now have our two key numbers, the risk for the smokers and the risk for the non-smokers. The final step is to put them head to head to see what the real impact of that exposure actually is. This is the payoff. So here's the crucial comparison. On one side, we have the risk if you smoke. On the other side, we have the risk if you don't. The difference between these two numbers, that's what we've been working towards this whole time. And that difference has a name. In our smoking example, since it's a risk factor, we call it the absolute risk increase. It tells us exactly how much extra risk comes from smoking. Now, if we were studying something good, like a vaccine, this same subtraction would give us the absolute risk reduction. But either way, it tells us the real-world impact of that exposure. So why do we do all of this? I mean, why is this calculation so important? To get that, we have to talk about the fundamental starting point of all science, something called the null hypothesis. It's the default, skeptical assumption that there's no relationship at all between the things we're measuring, that smoking, for example, has zero effect on lung cancer. And this is where our 2x2 table comes full circle. The entire process, organizing the data so carefully, calculating the risks, finding the difference, it's all about one thing: gathering evidence. The researcher's goal is to find enough strong evidence to be able to confidently reject that null hypothesis and say, nope, something really is going on here. There is a connection. So, the 2x2 table gives us a really powerful first answer. But in science, as you know, every answer just leads to more questions. We've isolated one factor, but what else might be in the mix? What about age or environment or genetics? That's the next step in the investigation, and it all begins with the incredible clarity you get from this simple box. Thanks for joining this explainer.